Okay, I'm recording now. So we know that we have a methyl group somewhere and two methyl groups somewhere that are the same, right? The one methyl group is one, and then the two methyl groups are the same. We know we have a carbonyl. We got to put that nitrogen in there somewhere. And we don't see any H's on a nitrogen from our NMR. These are just methyl groups. So how are we going to put this together? Olivia and Kiara, you guys have already solved this. What did you guys do next?
Can you put the one carbon, another carbon attached to either side, and then off of that, put the two methyl groups?
So you want another carbon here?
Yeah.
With two methyl groups?
Yes.
Now we need another bond here, and we still have a nitrogen.
And then next to the nitrogen, another carbon.
Okay. Now, how many carbons are in your molecule right now?
4.
I see 5. I see 5.
Oh, yeah. Okay.
Okay, so this isn't going to work. Kamal?
Could you just like erase that carbon and leave that N?
So, okay,
Yeah.
so you want...
Like, can you just like do the same thing and then just stop when you drew the nitrogen?
So put a carbon here and then 2 carbons here?
Yeah.
And then put the nitrogen here?
Yeah.
Okay, what's the formal charge on that nitrogen?
Negative.
Does it have any lone pairs?
Oh no. Yeah, it should.
How many bonds does nitrogen like?
3.
It's neutral. 3 bonds and a lone pair. Right now we got 4 carbons and a really pissed off nitrogen.
So what if you put...
And this carbon right here is not a methyl group. This one right here is a CH. So that's going to be split. That would be like a huge multiplet.
I
have a question.
Oh, go ahead.
Thank you. Can you put the oxygen double bonded to the nitrogen or no?
Well, in the IR, it showed that we had a carbonyl, which is a C double bond O.
So you can?
You cannot.
Okay.
I did, so I had like nitrogen, and then to either side of it, I had a methyl and a methyl.
On the nitrogen?
Correct. So then the nitrogen was satisfied.
Now it has 3 bonds. Good.
And then off of that carbon, I had another methyl group.
So now does this match?
Yeah.
If we label this as peak A and this as peak B, A is going to be this one. 3 hydrogens on a carbon next to one with none. And over here, these 6 are going to be B. We have 2 methyl groups on an atom next to one with none, right? 3 H's here and 3 H's here, so that's 6 H's total on a carbon next to an atom with none. We have a carbonyl, and we have 1 oxygen, 1 nitrogen, and 4 carbons, and 9 hydrogens, okay? So if we look at the carbon NMR, now we're labeling the carbons, not the hydrogen. So if this is A, that's going to be this one. See that? Because if you look at the table, carbonyl amide is going to be way up near 180, and that's A. So now the one right here, so I'll do, this is B and C, and then this is D. So this methyl group is D. This carbon right here is D. This carbon is less electronegative than nitrogen. And so now we have B and C that are going to be these 2 groups right here. And the reason that they're different and not the same is that this compound has a resonance structure. And so sometimes this is a double bond. And then this is a partial double bond. And so those 2 are different. A minor detail that you don't really have to worry about, but that's why there's 2 peaks down there. Is because sometimes there's that resonance contributor makes that molecule, this area right here, more planar, so that this group and this group are in different environments. Okay? But right here is your self structure that's completely labeled. For full credit, you need to label A and B, and then you need to label A, B, C, D, and then put them on your molecule. And then we already labeled the IR as being carbonyl peak and the sp3 hybridized carbon.
So where is the B and the C on the red?
This one's probably going to be the B one because it's shifted further downfield. It's deshielded because of the oxygen right nearby.
Can we do like one?
Number one?
Just get like a baseline for a carbon NMR. Like we kind of already did it, but.
I have some questions. I know that like alcohol is like the smooth tongue and benzene is the jigsaw, but I have trouble like remembering. So we need to know about the downward so those the alcohol's a downward tongue limit. We need to know about downward and upward like peaks and like if they're on the left, right, or middle and stuff. Although the far right's fingerprint, which we don't need to know, but I have trouble knowing the shapes of all functional groups. It's a lot of it's about memory. You said in the expertise, like I mean. Like I want to know the shape of all functional groups and how to know that, and like if it's up or down peaks and left or right or middle.
So you will never have up peaks. In IR, you will never have up peaks. They're only down. And you logged in late, but I did show that. I'll do this super quick, and then I'll get to your question number one, Kiara. This would be an alcohol.
Okay.
This would be a carboxylic acid, like some crazy, I guess that's not, more like this.
Right. Okay.
That's a carboxylic acid. This is a carbonyl, and those are the main ones. And then the jigsaw for the benzene.
I don't know how we know that, but
those are the main ones. But Kiara, before you started talking, Kiara asked about question number one, so I'm going to do that, and then I'll come back to you, Jacob, okay? But you'll never have a peak going up on IR when the spectrum is in transmittance mode.
Right, because the line is up, so it's down.
If you have a peak going up on IR, you should redo it and do a background first.
Okay, because like, so the jigsaw's multiple down peaks, not up and down peaks. And they're down peaks only because the line in general starts at the top.
Yes.
Okay, that makes sense then.
Okay, Kiara, question number one for carbon. We have C5H12. And there's no integration for carbon. It's just kind of like, almost kind of like the size of the peak, but it's just estimated. And there's no splitting in carbon. So this is just basically that there's 3 types of carbon with C5H12. If you figure out the degrees of unsaturation, what's that? Degrees of unsaturation for this one?
What was it? 5 by 2? That's not right.
10. 10 times 2.
Oh, thank you.
Plus 2. Plus 12.
Yes, plus 2. My bad, 12. I was like, wait a second, what?
12 minus 12.
So it's 1.
So 12 minus 12 is 0. 5 times 2 plus 2 is 12. So you write that over here. And how many hydrogens do we have? We have 12. So 12 minus 12 is 0. Okay, so there's 0 degrees of unsaturation. So we know we have all carbons that all don't have any double bonds and no rings. And we have 3 different types of carbons. I just start drawing stuff. I just start trying to put it together. So I could have like, I'm so sorry, 1, 2, 3, 4, 5, and then I could do 4 with like this, or that. So it's got to be one of those.
The mountain one.
The straight chain.
Yeah.
Yep. And so if we're going to label this, if this is A, this is B, and this is C, this is going to be C, B, A. You can tell because A is shorter. So it has less carbons. These are like twice the size, so they have 2 carbons each. As you get more and more carbons, you're going to be shifted downfield. So this carbon right here has 3 hydrogens on it and only 1 carbon. So that's going to be the furthest upfield, the lowest number.
Okay.
Okay?
I'm a little confused on that one.
Yep.
because of the, like, I know with the hydrogen NMR, like with the signals, how do you do the carbon NMR? Like,
So carbon NMR is less informative and it's also so much easier. With carbon NMR, you just look at the number of different signals. So there's literally 3 different types of carbon. And 2 of them have more carbons than the 1. And that's all I can really tell you that I get out of carbon NMR. It's not as helpful as the proton NMR.
Could you explain how you find your neighbor, like the neighbors?
So that's in proton NMR. Let me finish this one.
Okay.
Okay, so do you see that, Kiara? There's 3 different peaks. So that means there's 3 types of carbon, but these 2 are taller than that one. So if this is 1 carbon, then these are each 2 carbons each. So there's no integration, but you look at peak height a little bit to get an idea. So
can you repeat that part where it's 2 carbons?
If there's a total of 5 carbons, and I only have 3 peaks, some of my peaks have to mean 2 carbons.
Yeah.
Right? Because it only adds up to 3, but I need 5. So there's going to be 1 here, 2 here, and 2 here to equal 5. And the way we tell that is because of the peak height. Right? This one is shorter than these 2.
Okay.
All right?
Do they always have to go in order? Like, you know how you put like A, B, C, like in number 1 in like order, or can like A be on like one end or C be on the other?
So it's however you label your molecules. So you could do CBA, you could do ACB, like you can label them anyway, as long as this carbon is directly correlated to the peak that it represents. And this, you can go in any order. You can number them 1, 2, 3. You can put Greek letters, just so that you're saying this carbon is responsible for this signal. This carbon is responsible for this signal.
You said there's 3 types of NMR. There's carbon and proton, which means hydrogen, I think. And then there's a 3rd type?
No, just 2. There's a million different types of actual NMR, but in this class, we're going to do carbon and proton, or carbon and hydrogen.
Does it matter like if the groups are on the left, right, or middle?
No, you can draw it any way as long as it's connected the right way.
All right, what else do we need to know for NMR for like the test in the lab and stuff?
Well, you have to turn in this worksheet.
Oh, when does it due? Oh, next week in lab?
Yes.
Okay, that sounds good, so I'll try to do that.
Kamal, if we talk about splitting and neighbors, okay, so I think question number 6 is a really good example to teach about splitting and neighbors. Okay, so let's do number 6. Even if you've already done it, I'll walk through how I would do it. Degrees of unsaturation.
0.
0. We have 2 carbons, 6 hydrogens, and an oxygen. Okay? So, and there's 0 degrees of unsaturation. I look at this peak right here, and here's how I do this. I have 3 hydrogens. Remember, those 3 hydrogens are the ones responsible for this peak. 3 hydrogens on a carbon next to one with, and then I look at the splitting. And do you see that this is a triplet?
Yep.
1, 2, 3. So I have 3 peaks. I have a triplet, which means that I have 2 hydrogens on the neighboring carbon. It's always, the number of peaks is n plus 1. So if I have a triplet, that means there's 2 hydrogens next door. So to finish this thought process, I have 3 hydrogens on a carbon that's next to a carbon with 2. And the reason I say that it's next to one with 2 is because of the splitting. So this CH3 is here, and then I'll change colors. This CH2 is because of the splitting.
And you said the number of peaks is n minus 1?
However many peaks you have,
Mhm.
is going to be one more than the number of hydrogens next door. So you have your number of peaks.
Oh.
You have 3 peaks. You subtract 1. So there's 2 hydrogens next door.
Okay.
So a triplet means you have 2 next door. A doublet means you have 1 next door. A singlet means you have 0 next door. A quartet means that you have 3 next door. And if you have a multiplet, like huge, like 7, that means you have 2 methyl groups, 6 next door. It's always n minus 1. The number of hydrogens is n minus 1 compared to the number of peaks that are split. Okay? So now let's go do the other one. I'm working with this peak right here now. I have 2 hydrogens on a carbon. So I'm going to do this, CH2, 2 hydrogens on a carbon that's next to one with, and there's 4 here. So I have 3 neighbors. I have 3 hydrogens on my carbon next door. The CH2 comes from here, and the CH3 is because of the splitting. Now, if you're looking at this saying, but I only have 2 carbons, how could I possibly have both of these? These are the same. These are the same. In one case, the signal in red is telling us about the CH3s. And then the other one, the signal in green, is telling us about the CH2. And it's the same. So I know I have a CH3 next to a CH2. But I'm not done. What's missing?
OH.
The OH.
You have an OH. Well, that's that peak right there. The H signal from an OH is always going to be little stubby thing that's kind of like, it's anywhere from 1 to 5, I think. It's like, so that's my OH peak right there. So you'd label this OH to get full credit, and then you have to put your OH here. And now that totally makes sense because our CH2 is shifted further downfield because it's closer to the oxygen compared to our CH3. And the OH is always variable, like where it is, where it shows up. So now for complete full credit on this one, what am I missing?
The structure.
So here's the structure. This is A. This is A. I'm going to go with Olivia. This is D. You can label it whatever you want. This is D. And then this is X. And this is X. So you don't need to do A, B, and C in order. I just labeled it funny stuff. I hope that didn't confuse you.
No, you're fine. I'm just like trying to figure out. So like the final answer is CH3, CH2, OH, and then then you just score. Okay, because everything was jumbled. I was trying to figure out.
Yep, this CH3 came from this signal right here. CH2 came from this signal right here, and the OH came from this signal right here.
Perfect.
Okay.
Well, like for 7, like I have the answer, but how would you label it correctly? Because I know it's like CH3, O, CH3. How would you label it like the A?
Oh, that's a fun one.
Yeah, because it's a singlet.
It's a singlet. That means there's 6 hydrogens that are exactly the same.
Yeah.
So the way that you would draw this, and I'm not going to draw my CHs out because it's easy. This is my answer. All right.
Can we do 14?
Anytime I see anything in between 6.5 and 8, it means that I have a benzene ring. Oh, but before that, we have to do degrees of unsaturation. 13 times 2 is 26, plus 2 is 28. How many hydrogens do I have?
Oh, you have 10 hydrogens.
10.
So what's left over?
18.
18
divided by 2.
Divided by 2.
9 degrees.
Yikes, 9 degrees.
It's a lot.
Okay, now, what did I tell you over here?
Benzene ring.
How many carbons do I have?
13, so that means there's going to be 2 benzene
2
rings.
benzene rings. How many degrees of unsaturation is each benzene ring?
4.
Yeah, 4.
4.
Oh,
ring,
oh, that's right.
double bond, double bond, double
Right.
bond. But if we need 13 carbons, then I'm going to say maybe we need 2 benzene rings. 2 benzene rings. How many degrees of unsaturation is that? 4 and 4. So that's 8 total. So we only need 1 more degree of unsaturation. And there's only protons on the benzene ring. There's no peaks down here or anything like that. That means that I have 5 hydrogens on each. I'm just going to draw the line for now, so I don't have to draw all the H's. I have 5 H's on each of my benzene rings, which would be 10 total H's. So we have 1 space that's left on each benzene ring because there's only 10 hydrogens and there's 6 carbons. So I need something here and I need something here. And what are we missing in terms of carbon?
That 1 carbon.
We have 1 carbon and we have
Oxygen.
1 oxygen and we have 1 degree of unsaturation. How could we put a carbon and an oxygen and 1 degree of unsaturation on this molecule?
Carbonyl.
I'm feeling really guilty about not putting H's on. So you know what I'm going to do? I'm going to erase. I'm going to erase them. So y'all know. If you draw those bonds, you have to put the H's or you get it wrong. Okay, now does this make sense? Let's look at the carbon NMR.
It like shows that what double bond.
A whole bunch of stuff on the benzene, right? If you look at your table, in between 120 and 140 is all the carbons that are in a benzene. But then there's this one up near 200. What's that one mean?
There's a double bonded, which is a carbonyl
The
between the
carbonyl.
200 and 150.
The carbonyl, yep. So we'll label this as X and this as Y. And then this is going to be Y, all of these. And then this is going to be X. And then up top, this is going to be A. And then all these protons are going to be A.
So essentially Y and A are the same.
Y is talking about the carbons.
And then A is
A
talking
is talking about the hydrogens off the carbons. Yep.
On the test, are we gonna have to like label X, Y, A, or just like put the variables? Okay.
For full credit, every single one of my questions is going to say, and label the spectra for full credit. I don't have it in this worksheet, but on my exams, it'll say for full credit, label the spectra. And I'm sure Dr. Teich is going to require the same thing. Kiara, have you asked for any specific ones you wanted to do yet? Or Olivia? Did 1.
Can we go over 15?
15, I have to tell you, is very similar to 14. How many degrees of unsaturation in this one, though?
8.
8.
8. So we have 2 benzene rings, right?
Yeah.
But we don't have a carbonyl in between. We have something else in between. And that shows here too. There's the 10 H's in between 6.5 and 8. And we got the boatload down here. Now there's not one up here. So we don't have the carbonyl. So what do we have?
A single bonded O. Like an alcohol kind
An
of.
alcohol. That's exactly what we have. I'm going to start getting fancy here and drawing my shorthand stuff. So that's shorthand way to draw benzene. You know that, right? And then that's exactly what it is, an OH. So now what we have to label here is, can you see yellow? So the 10 H's is easy. That's going to be A, and that's going to be all those. And then we have an H here that we have to label and an H here that we have to label. So it turns out that this is the alcohol peak, OH. So I'm going to call that B, just because I like to go in order as much as Olivia doesn't. I'm just giving you a hard time. And then this is C, which is going to be this one right here, C. And if we looked at the carbon NMR, this carbon right here is going to be X. And then all of these are going to be Y. And then that's these. Whoops, sorry, Y. This one up here, that's part of the benzene.
So the carbon NMR will always have like the 0 to 200 scale.
Yep.
Okay. Yeah.
Yep. Proton NMR is always 0 to 12-ish. And then the carbon NMR is 0 to 220. Any other questions?
For 17, isn't IR the best because like you get those alcohol peaks? There's no specific one.
There's no specific correct answer. If you argue your point, you can use any of the techniques.
So I can just say like there's no specific one. They all like show their own individual.
Oh no, it says which one do you think?
Oh, okay. Okay.
So you pick one that you like and then explain it away, but there's no wrong answer unless you can't explain it, right? It says discuss the strengths and weaknesses of each technique.
What's the thought process behind 16?
So question number 14 and question number 15. So compound in number 14 can be reacted to become number 15. So we can take the carbonyl and make it the alcohol. So how are we going to use NMR to determine that we're getting product? And I would argue that as you start seeing this peak and this peak appear, you know that you're getting product because this one doesn't have them. And then same with the carbon one. You're going to see this one appear and this one disappear.
So just like monitor their peaks, like each both have their own distinct.
Yep. And as you see the transformation of the spectra, you know that the chemical reaction is happening.